Hello, I'm Stephen Turrell. I'm a postdoctoral research associate in the Pasteur Group at the University of Oxford. And I'm going to be talking about physical vapour deposition and how I use that in my research on thin film batteries. So, what is physical vapour deposition? Well, PVD, or physical vapour deposition, incorporates a couple of different techniques. So the key techniques are evaporation and sputter deposition. So evaporation is used in various different industries, but it's particularly used to deposit metal layers on plastics for food packaging, for example. And sputter deposition is used in several other different industries, particularly the semiconductor industry. It's used to make integrated circuits, and also in the optics industry for anti-reflection coatings on glasses, and for touchscreens for a wide variety of different electronic devices. And the photo here shows one of our systems in the Centre for Energy Materials Research, and one of the benefits of our PVD system is that it's contained in a glove box, so we can use it to deposit air-sensitive materials. So I'll just go over the first technique, the first main PVD technique, which is evaporation. And evaporation is fairly easy to understand. You put the material that you want to evaporate in a boat, and then you heat that boat up in a vacuum chamber, and then the vapor that's produced rises to the top of the chamber and it deposits on a substrate. And one of the benefits of evaporation over other kinds of PVD techniques is that it has a relatively high deposition rate, so you can achieve fairly thick films in a short space of time. So one of the other key PVD techniques is magnetron sputtering, and there are many similarities between magnetron sputtering and evaporation, but there are also some differences. So you start with the material that you want to deposit as a target in either powder or a sintered pellet form. That target material goes into a PVD chamber, a vacuum chamber, and to produce a vapor phase, argon or another gas is flowed into the chamber. That gas becomes ionized. The positive gas ions collide with the target, and that causes sputtering of the target material, and the atoms and ions of the target material travel up through the vapor phase and condense on the substrate, building up a thin film. So how is PVD applied to battery fabrication? Well, the typical solid-state battery has 3 layers. For a lithium metal cell, there's the lithium metal anode, the solid electrolyte, which is normally a ceramic, and the cathode, or positive electrode. And in a conventional solid-state cell, these cells are typically hundreds of microns thick. But if you use physical vapor deposition, you can make a cell in a layer-by-layer fashion that's less than 10 microns thick. So there are some obvious benefits of that if you need a very small battery for applications such as wearable electronic devices or implantable devices, or perhaps very small-scale sensors and actuators. Then this technique can make those cells. But there are some other benefits. For example, you can get very high-quality solid-solid contact between the layers if you deposit using PVD. PVD techniques also lead to very low defect densities and very high relative densities. And that means that the energy density of the cell is maximized. It also means that defects which might act as sources of failure during cycling are eradicated, so that leads to better cycling performance. And another advantage is the fact that the solid electrolyte layer is made very thin. And the solid electrolyte is typically has a lower ionic conductivity than the liquid electrolytes that are used in many conventional lithium-ion batteries. So by making the solid electrolyte layer very thin, you minimize the contribution to the overall cell impedance. And as I said earlier, one of the additional benefits that we have in the Centre for Energy Materials Research is that we have PVD systems inside glove boxes. And battery materials are often very air sensitive, so being able to do the deposition inside a glove box means that we don't have to expose these materials to air. So just a bit about my research. So I work on thin film electrolytes and electrodes, and I've just included a couple of photos to illustrate what I do. So at the top is a photo of midway through making a thin film cell. So I've deposited this solid electrolyte layer using magnetron sputtering. I then mask a sort of circle on top using Kapton tape, and then I deposit my electrode layers on top. And it's important to be able to define an area for the electrode by masking, because otherwise there could be short circuiting at the edges between the top and bottom electrodes. So that's why we use masking. And at the bottom I included an image, a scanning electron micrograph image showing an LCO cathode layer that I deposited by magnetron sputtering. And on top of that there's a lithium phosphorus oxynitride electrolyte layer. And I included this to show how good the solid-solid contact is when you use sputter deposition. You get a really conformal layer that follows the undulations of the underlying LCO, lithium cobalt oxide layer, and you get better solid-solid contact than you could using bulk synthesis techniques or bulk fabrication techniques. So to summarize, there are many applications of physical vapor deposition in industry. There are also applications in battery research, one of the key ones being that you can make very thin, very small batteries, but there are other reasons why you want to use PVD to get very high quality interfaces and electrode and electrolyte layers. And the system that we have in the Center for Energy Materials Research has the additional benefit that we can use it inside a glove box and avoid exposing our very air-sensitive materials to the atmosphere. So I'd like to finish by acknowledging the equipment provided by the Department of Materials at the University of Oxford and funded by the Henry Royce Institute and also the Faraday Institution Solbrat project. And I'd also like to thank my fellow group members in the PASTA group. So thank you for listening.